Okay, so welcome to another deep dive. And today we are looking at building demanding Python applications. Specifically, we are going to be talking about concurrency and cloud deployment. And for this deep dive, the source material we're going to be looking at is actually kind of interesting. It is an excerpt from a detailed mock interview transcript with a Python expert.
Okay, interesting.
Yeah, so I mean, hopefully it'll be a good source for us. We're going to be looking specifically at how to handle CPU-intensive tasks, how to use asynchronous programming in Python, and then, once you have that application built, how do you deploy it to the cloud? So we'll be looking at major cloud platforms like AWS, Azure, GCP. Yeah, so let's jump into it. I guess right off the bat, what really struck me when reading through this interview transcript was just how practical the expert's advice seemed. It didn't seem like they were just, talking about theory. It seemed like they had real experience, solving these kinds of problems in Python, and I think that's really valuable.
Yeah, for sure. I mean, it's always great to hear from people who've actually, been in the trenches and dealt with these challenges firsthand. That practical experience is invaluable, I think, especially in a field like software development where things are constantly changing and evolving. It's so important to have those real world insights.
Yeah, absolutely. So let's start with CPU-intensive tasks. This is something that a lot of Python developers, kind of run into at some point. As you start building more complex applications, you realize, oh, some of these tasks are really putting a strain on the CPU. And one of the first things that people usually learn about is the global interpreter lock, the GIL, in CPython. And how that kind of puts a limit on your ability to achieve true parallelism when you're dealing with these CPU-bound operations.
Right, right. I mean, the GIL is, it's kind of like a necessary evil in CPython. It's there to protect the integrity of the Python interpreter, but it also means that you can't really run multiple threads truly concurrently on different CPU cores. They're all kind of fighting for that one lock. So if you have a task that's really CPU bound, like let's say you're doing some heavy number crunching or image processing or something like that,
Right.
just relying on threading might not give you the performance gains you're looking for.
So, threading isn't always the answer when you're dealing with these CPU-bound tasks. So what did our experts suggest?
Well, they highlighted multiprocessing as a key technique,
Okay.
and specifically the multiprocessing .pool module
Hmm.
got a lot of attention. And this is, it's really a way to kind of work around that GIL limitation because what it does is it lets you spin up a bunch of separate Python processes. And each of these processes has its own independent Python interpreter and its own memory space. So they're not all fighting for that same GIL. They can actually run, truly in parallel on different CPU cores.
I see.
And what's great is they didn't just talk about it in theory. They actually gave a concrete example from a fintech project they worked on where they were doing some image processing.
Right.
And by switching to multiprocessing .pool, they saw a 40% reduction in processing time, which is, that's a significant speed up.
It's huge. Yeah.
Yeah, and imagine, if you're doing something like fraud detection or high frequency trading where every millisecond counts, that kind of performance gain can be a real game changer.
Yeah, absolutely. And they also mentioned concurrent dot futures. How does that fit into this?
Right. So concurrent .futures is, you can think of it as kind of a higher level abstraction over threads and processes.
Yeah.
It lets you manage a pool of workers, either threads or processes, and you can submit tasks to that pool, and it'll kind of handle distributing those tasks and collecting the results for you. And it gives you some nice features like being able to set timeouts on tasks, being able to cancel tasks, things like that. So it can be a really useful tool for managing concurrency in your Python applications.
Okay. And then what about for those really large-scale distributed workloads?
Right. So, once you get to a certain point, you might need to go beyond just using multiple processes on a single machine.
Hmm.
And for that, the expert brought up frameworks like Celery. And Celery is basically, it's a distributed task queue. So it lets you define tasks in your Python code, and then you can send those tasks to a message broker. And then you have a bunch of worker processes, which can be running on different machines that are listening to that message broker. And when a task comes in, they'll grab it and execute it. And this allows you to really scale out your application across multiple machines and handle really large workloads.
So it's like having multiple workshops working on different parts of the same problem.
Exactly, yeah. And each workshop can be in a different location.
Okay, got it. So that's really interesting. So we've got some strategies for those CPU-bound tasks. Now let's switch gears a little bit and talk about asynchronous programming, which is really useful when your application is spending a lot of time waiting for things. Think
Yeah.
about things like network requests, database queries, file I/O, that sort of thing.
Yeah, exactly. And Python's Asyncio library is really well suited for this kind of I/O-bound workload. It allows you to write code that can handle multiple operations concurrently without blocking using the async and await keywords. So instead of your program just sitting there, twiddling its thumbs while it's waiting for a response from a server or a database, it can actually go off and do other things in the meantime, making much more efficient use of resources.
Right. And the expert provided a code snippet demonstrating a robust approach to handling errors and also incorporating automatic retries. And they were importing Asyncio, the logging module, and a library called Tenacity.
Right. Yeah. And I think that combination of tools is really smart.
Hmm.
Tenacity is a great library for handling retries. It has a decorator called retry, which lets you easily retry a function call if it fails. And they were using it with the wait exponential strategy, which means that each time it retries, it waits a little bit longer before trying again. So,
Hmm.
if you have a server that's temporarily down, it's not going to just hammer that server with requests. It's going to back off a little bit and give it some time to recover.
Yeah.
And then they were also using the stop after attempt parameter to limit the number of retries. So, if something is really broken, it's not going to just keep retrying forever.
Yeah, that makes sense. And within the actual function itself, the fetch data function, they were using asyncio dot wait for with timeouts for both establishing a connection and for actually reading the data.
Yeah.
Why is that so important?
Well, in asynchronous programming, you really need to be mindful of timeouts.
Yeah.
Because if you don't have timeouts, and let's say you're trying to connect to a server that's down or it's really slow, your program could just hang there indefinitely waiting for a response that might never come.
Oh, I see.
So by using asyncio.wait for, you're basically saying, hey, only wait for this operation for, this many seconds. And if it doesn't complete within that time, then just raise a timeouter.
Ah.
And that allows you to handle the error gracefully and maybe try a different server or do something else.
Right, right. And then within the try except block, they were not only logging the error with the traceback, but they also mentioned integrating with tools like Sentry. What's the value of having something like Sentry?
Well, logging is great for local development and debugging.
Yeah.
But when you have an application running in production, you really need a way to aggregate and monitor your errors. And that's where a tool like Sentry comes in. It's a dedicated error tracking and monitoring service. So you can set all your errors to Sentry, and it'll give you a nice dashboard where you can see all your errors. You can see how often they're happening. You can see the stack traces. You can see which users are affected.
Oh, wow.
And it can even send you alerts, if there's a spike in errors or if a new error starts occurring.
Yeah, that sounds really valuable, especially as your application grows and you have more and more users.
Yeah, absolutely.
And then in the finally block, they were making sure to close the writer and wait for it to close. Why is that important? Why do we need that finally block?
Yeah, so the finally block is really important for resource cleanup. Whenever you're working with resources like files or network connections, you need to make sure that you close them properly when you're done with them. Otherwise, you can end up with resource leaks, which can cause your application to slow down or even crash. And in this particular case, they were using the writer.wait closed coroutine to make sure that the writer is actually closed before moving on.
Okay. And then finally, the main asynchronous function showed how to kick off multiple tasks concurrently using asyncio.create task, and then wait for all of them to complete using asyncio.gather. And they also had this interesting argument, return exceptions equals true.
Right. So asyncio.create task is basically how you create an asynchronous task in Asyncio.
Okay.
And then asyncio.gather lets you run multiple tasks concurrently and wait for all of them to complete. And the return exceptions equals true argument is really useful because it means that even if one of the tasks raises an exception, the other task will still continue to run and you'll get all the results or exceptions back in the list.
Gotcha. So it doesn't just, bring the whole thing crashing down if one of them has an error.
Exactly, yeah.
Okay, cool. So that's a really interesting look at, how to use Asyncio and handle errors and retries and things like that. So let's move on now and talk about deploying these applications to the cloud. And let's start with the big one, AWS. So the expert talked about different deployment strategies depending on the type of application.
Yeah, they really emphasize that, yeah, there's no one-size-fits-all approach to cloud deployment. It really depends on the specific needs of your application. So for those long-running stateful APIs, the kind that need to maintain some kind of persistent state, they recommended using either ECS, Elastic Container Service, or EKS, Elastic Kubernetes Service, within a virtual private cloud, a VPC, with all the security groups and an application load balancer and everything.
Okay. And for those who are maybe not familiar with AWS, can you just explain what those things are?
Sure, yeah. So ECS and EKS are both ways to run Docker containers on AWS. ECS is kind of the simply option. It's AWS's own managed container orchestration service, and EKS is basically Kubernetes running on AWS. So it's a bit more complex, but it also gives you a lot more flexibility and control. And a VPC is it's basically your own private network within AWS. So it's isolated from the public internet, and you can control exactly which traffic is allowed in and out. And an application load balancer is basically a load balancer that sits in front of your application and distributes traffic across multiple instances of your application.
Okay. And so for event-driven applications, what did the experts suggest?
Yeah, so for those kind of applications that are reacting to events rather than that constantly serving requests, they recommended AWS Lambda. And they specifically mentioned webhook processing as a good use case for Lambda.
Okay. And can you just explain real quick what Lambda is?
Yeah, so Lambda is AWS's serverless compute platform.
Okay.
So it lets you run code without having to manage any servers. You just upload your code, and Lambda takes care of everything else. It'll scale it up and down automatically based on demand, and you only pay for the compute time that you actually use.
Okay. And they had some tips for optimizing Lambda deployments.
Right. So they talked about using the serverless framework and AWS SAM, which are both infrastructure as code tools that can help you manage your Lambda deployments.
Yeah.
They also talked about the importance of reducing the size of your Lambda deployment package, because the larger your deployment package, the longer it takes to upload and the longer it takes to start up.
Yeah.
And they specifically mentioned using Lambda layers, which allow you to share common dependencies between multiple Lambda functions. So you don't have to include them in every function's deployment package.
All right.
And they also talked about using provision concurrency to reduce cold starts.
Right.
Which is, when a Lambda function hasn't been run recently and it has to start up from scratch, that can take a few seconds.
Right.
So provision concurrency basically lets you keep a certain number of instances of your Lambda function warm and ready to go. So when a request comes in, it can be handled immediately without having to wait for the function to start up.
Okay. So they gave a specific example of reducing cold start time from 3 seconds to 500 milliseconds during peak hours.
Yeah, exactly. Which is a huge improvement.
Yeah, it's a big difference. Now, when would you choose ECS or EKS over Lambda for a high-throughput service?
Right. So they said that for applications with consistently heavy traffic, like if you have an API that's constantly being hit with requests, ECS or EKS might be a better choice because they give you more control over your underlying resources and they integrate better with CI/CD pipelines. Whereas Lambda is really good for those kind of sporadic event-driven workloads where you don't need that constant high throughput.
Okay. And then moving beyond AWS, let's talk about Azure and GCP. So how does the expert approach managing deployments across multiple cloud platforms?
Yeah, so they basically said that, while each cloud provider has its own set of services and tools, the fundamental principles of writing good code, secure, scalable, efficient code, those remain the same, regardless of the platform.
Right.
So on Azure, they talked about using Azure Functions, which is their serverless compute platform.
Okay.
And they mentioned that they use extension bundles to package up their dependencies, and they use Azure pipelines for CI/CD.
Okay. And what about GCP?
Yeah, so on GCP, they talked about using Cloud Functions, which is their serverless compute platform.
Right.
And they also mentioned using Google Kubernetes Engine, GKE, which is their managed Kubernetes service.
Okay. And they went into a bit more detail about deploying on GKE.
Right. So they talked about the importance of configuring horizontal pod auto scaling, HPA, which basically allows you to automatically scale the number of pods in your Kubernetes cluster based on CPU usage or memory usage or even custom metrics.
Okay.
They also talked about using vertical pod autoscaler, VPA, which can automatically adjust the resources allocated to each pod based on its usage patterns.
Okay. And then they also mentioned Kita.
Yeah, so Kita it's an open source project that allows you to do event-driven auto-scaling on Kubernetes. So you can basically scale your application based on events coming from external sources like message queues or cloud services.
Interesting. So it sounds like each cloud platform has its own strengths and weaknesses.
Yeah, definitely. AWS has a really mature serverless ecosystem.
Yeah.
Azure has really good integration with Microsoft tools and services, and GCP has really strong Kubernetes support.
Okay. So it's really about choosing the right platform for your specific needs.
Yeah.
Now, let's talk about operational and security rigor. This is something that's often overlooked, but it's absolutely critical for building demanding applications. So the expert shared some interesting examples from their own experience.
Yeah, so they talked about how they used SQL Map to identify a potential SQL injection vulnerability in an older part of their code base. And they fixed it by refactoring the code to use parameterized queries with Alchemy Core.
Okay. Can you just explain why parameterized queries are so important for security?
Yeah, so basically with parameterized queries, you're separating the SQL code from the data.
Okay.
So instead of directly embedding user input into the SQL query, which is how SQL injection vulnerabilities happen, you're passing the data as separate parameters. And the database driver then takes care of escaping the data properly.
Yeah.
So even if the user tries to inject malicious SQL code, it's not going to be executed.
Okay, so it's much more secure.
Yeah, much more secure. They also talked about enforcing WASP top 10 security checks through Git hooks in their CI/CD pipeline,
Okay.
which is a really good way to prevent security vulnerabilities from being introduced in the first place.
Right, yeah, you're catching them early.
Exactly, yeah.
And they also talked about using SNCC scans to block deployments if critical CVEs are detected.
Right. So Snake it's a security scanning tool that can identify known vulnerabilities in your code and your dependencies, and by integrating it into your CI/CD pipeline, you can automatically block deployments if any critical vulnerabilities are found.
So it's like having an automated security guard.
Exactly, yeah.
And they also talked about using AWS Guard Duty to monitor their AWS environment for suspicious activity.
Right. So Guard Duty it's a threat detection service that uses machine learning to analyze your AWS logs and identify potentially malicious activity.
Okay.
So it can help you detect things like unauthorized API calls, unusual network traffic patterns, attempts to exfiltrate data.
And they saw a 90% reduction in vulnerabilities during a subsequent PCI DSS audit after implementing these security measures.
Yeah, which is, that's a huge improvement.
It's amazing, yeah.
Yeah.
Okay, so let's move on to ensuring stability and performance. They gave an example of their approach on GKE using a multi-layered monitoring strategy.
Right. So they talked about setting up custom Prometheus metrics to track key performance indicators like request latency, error rates, queue depths.
Okay.
And they visualize those metrics on Grafana dashboards, which gives them a nice, real-time view of the health of their application.
Okay.
And they also set up alerts, so they get notified if anything goes wrong.
And they also enforce strict resource limits on their Kubernetes containers. Why is that so important?
Well, if you don't set resource limits, then a single container could potentially consume all the resources on a node, which could lead to performance problems or even outages for other applications running on that node.
Gotcha. So it's about making sure that everything plays nice together.
Exactly, yeah.
And they also mentioned using profiling tools like PySpy for debugging issues like memory leaks.
Yeah, so PySpy it's a really useful tool for analyzing the performance of your Python code. It lets you see which functions are taking the most time, which objects are using the most memory, that kind of thing. And it's really helpful for identifying and fixing performance bottlenecks.
Okay. And how do you go about debugging memory leaks specifically in Python containers under production loads?
Right. So they said that the first step is usually to detect the leak, which you can often do through container level monitoring. So if you see the memory usage of your container steadily increasing over time, that's a good sign that you might have a memory leak.
Right.
And once you've detected the leak, then you can use profiling tools like PySpy or Memory Profiler to try to pinpoint the source of the leak. And often the solution involves refactoring the code to ensure proper resource cleanup. So making sure that you're closing files, closing connections, releasing objects when you're done with them.
Right. And they gave an example of a memory leak that was caused by persistent database connections not being closed properly.
Yeah, exactly. And they were able to fix that by simply ensuring that the connections were being closed properly.
Okay, so it's often these seemingly small things that can have a big impact.
Yeah, absolutely.
Okay, so finally, let's recap the key considerations when deploying Python services across AWS, Azure, and GCP, focusing on scaling, latency, and security.
Right. So they basically reiterated that, each cloud platform has its own strengths and weaknesses.
Okay.
AWS has a very mature serverless ecosystem with tools like Lambda, CloudWatch, GuardDuty.
Right.
Azure has really good integration with Microsoft tools and services, and GCP has strong Kubernetes support with GKE, HPA, VPA, Kita.
Hmm.
But regardless of which platform you choose, the key is to focus on writing secure, scalable, efficient code, and to make sure that you have proper monitoring and alerting in place.
So those are the non-negotiables.
Exactly. Yeah.
Okay, great. So to recap our deep dive today, we've explored strategies for handling concurrency in Python using both multiprocessing and Asyncio. We've looked at cloud deployment options on AWS, Azure, and GCP, and we've talked about the importance of operational and security rigor.
Yeah, and I think what's really interesting here is seeing how all these different pieces fit together. It's not just about writing code. It's about building and deploying and operating and securing complex applications in the cloud.
Absolutely. So our final thought for you, the listener, is this. As cloud technologies continue to evolve and Python continues to gain popularity, what new challenges and opportunities do you see on the horizon? And how can you best prepare yourself to stay ahead of the curve? Thanks for joining us on this deep dive.